Welcome back. Today we have some more examples of Gaussian elimination, which is the process that takes our matrices to row echelon form, and then Gauss-Jordan reduction. I don't believe I introduced that term, but that's the process where we continue from row echelon form to reduced row echelon form. And so you'll notice I have two matrices here. These are actually the same matrix, other than the fact that this one on the right, if you recall, is a homogeneous matrix. So there is a fourth column of zeros here on the right that is just implied. And so if we think of these two as systems of linear equations, then the coefficient matrices, coefficients for x, y, and z in all these linear equations are the same for the left matrix as they are on the right matrix. But the only difference is on the left matrix, those linear combinations of x, y, and z with these coefficients are equal to 1, -2, and -1. But in this matrix on the right, all those linear combinations are just equal to 0. So we call this matrix on the right the associated homogeneous matrix to the one on the left. This is the associated homogeneous matrix. So we're going to solve both of these, compare their solutions, see what the solution of the associated homogeneous matrix says about the solution to this one. So to start, I'm going to take -3 of row 1 and add that to row 2. I'm going to take -4 of row 1 and add that to row 3. First row remains unaffected. The second row changes in the following way. And the third row ends up being the same as the second row. And as a result, if we take negative row 2 and add that to row 3 is completely eliminated. It becomes a row entirely of zeros. And so as a result, this third row, because it was redundant, is effectively the same thing as having this trivial row down here, which really gives us no information. This just says that 0x plus 0y plus 0z equals 0, in which case x, y, and z could be anything. And so if we declare that z, for example, was the free variable and then used back substitution where the values of x and y depended on z, then we would have infinitely many solutions, because you can think about our equations as pieces of information, or rather constraints placed upon our variables. And if we only have two constraints placed upon 3 variables, then we have more variables than we have constraints to account for, and as a result, the set of variables that could meet those constraints is infinite. But we're going to continue anyway. So to take this to row echelon form, we'll take 1/6 of row 2. We'll have this matrix. And that's row echelon form. Now we'll take it to reduced row echelon form by taking 2 of row 2 and adding that to row 1. This is our result. Now let's look at this bottom row here. So again, this says that 0x plus 0y plus 0z is equal to 0. So this really makes a trivial statement about any of these 3 variables, and so we can choose one of them to be the free variable. So we're going to choose z here. We're going to say that this equation says that 0z equals 0, therefore z is any real number, because this applies to any real number. We can go back into row 2 here, because even though this is in reduced row echelon form, we still have to do some back substitution. Because we don't have a main diagonal of 1s, you'll notice we have this 0 right here, and so because of that, we can't eliminate this -5/6 or this 1/3. And so if z is any real number, y is equal to -5/6 plus 5/6 z, and x is equal to -2/3, which is the constant over here, and -5/6 was the constant for y, minus 1/3 z. These equations were just gotten from the matrix, and the solution set is x, y, z. We write our solution as a vector is equal to the set of the following vectors. So what this says is that x, y, z is equal to this constant vector plus this vector multiplied by z. Again, we interpret each of these rows as equations. These are just the equations that we got from our matrix in reduced row echelon form. If x was equal to -2/3 minus 1/3 z, then x, which is the first component of our vector which is equal to any vector in this set based on the value of z, the first component of the constant vector, which is in fact -2/3, just like we had here, plus z times -1/3, because that's the first component of this vector. And that is exactly what we see here, minus 1/3 times z. So the value of z parameterizes this, the value of z determines x. Similarly for y was equal to -5/6 plus 5/6 z, and y is going to equal the sum of the second components of these two vectors, and that is in fact -5/6 plus 5/6 z. Z, on the other hand, because we chose it to be the free variable, which is what we did over here, we could have chosen x or y, but we chose z because these other equations have leading entries in the x and y positions, so it just made sense to choose z as the free variable because it would be easy to solve for x and y. Z is equal to 0 plus 1 of itself, and that's exactly what we have here, that z is equal to 0 plus 1z. Now we're going to solve the homogeneous system, and we're going to see how that is similar, the associated homogeneous matrix. So of course, this homogeneous matrix is going to simplify in the same way that the coefficient side of the inhomogeneous matrix example that we just did simplified, because they're the same thing. This is the same as the coefficient matrix. The only difference is the constant column on the right, that fourth column here, is implied as a column of zeros, and therefore it won't be affected, whereas in the other one we started with some constants, and that's why it was not homogeneous or inhomogeneous. So if this reduced in the same way, then it's going to end up the same: 1, 0, 1/3, 0, 1, negative 5/6, 0, 0, 0. And so again, if we choose z to be the free variable, because this last row is trivial, it makes a trivial statement about all of these. It says x times 0 plus y times 0 plus z times 0 equals 0. And so that means that x, y, or z could all be any real number, but we're just going to choose z. Then y depends on z. Y is equal to 5/6 z. Based on this equation here, this says that y minus 5/6 z equals 0. Similarly, x is equal to negative 1/3 z. And so the solution set for this is going to look like the following. So yz, we write it in a vector, is equal to the set z times the vector negative 1/3, 5/6, 1, where z is any real number. So you'll notice that this is very similar to the solution set of the first matrix. You'll notice the solution set to the first matrix was the same, other than the fact that we have this vector right here. This part was the same as the solution to the homogeneous system, and so we call this the homogeneous solution because it's the solution to the associated homogeneous system. This is a particular solution. It is a specific solution based on a particular value of z, in this case when z is equal to 0. In that case, this vector is equal to 0, and we're just left with this one as the solution. So negative 2, 3, negative 2/3, negative 5/6, 0, that is a particular solution. We had many solutions that were described here. In fact, infinitely many solutions that were described with this set. They all describe this vector x, y, z. This is the general solution. So the general solution to any inhomogeneous system is equal to a particular solution, which is in this case the vector negative 2/3, negative 5/6, 0, which is based on the constants in that far right column that we had here, 1, negative 2, negative 1. And that particular solution in this case arises when z is equal to 0. And so the general solution for any inhomogeneous system based on the constants that we had in that far right column is equal to a particular solution plus the homogeneous solution, which is the solution to the associated homogeneous system. And so we say in general when solving a matrix that the general solution is equal to a particular solution, any particular solution, doesn't have to be when z is equal to 0, plus the homogeneous solution. That's the solution to the associated homogeneous matrix, the main idea of this video. So here we have another example, and now that we found the general solution for an inhomogeneous matrix for a matrix where we ended up having a redundant row, a row of only zeros, we had infinitely many solutions. Why don't we do this for two matrices where we're not going to have infinitely many solutions? So hint, hint, if this matrix on the left does not have infinitely many solutions, this matrix on the right, the associated homogeneous matrix, is also not going to have infinitely many solutions. And therefore, because it's a homogeneous matrix with only one solution, that one solution has to be the trivial solution, and this is a non-singular matrix. Therefore, the previous homogeneous matrix was singular. I'm going to start by taking negative row 1 plus row 2, and this is row echelon form. Now we're going to take negative 2 of row 2 and add that to row 1. And here we have the values. Here's the solution set. xy is equal to just the set of one vector, so we did have a unique solution. Negative 7, 3, explicitly the values for x and y. X is equal to negative 7, y is equal to 3. And now we're going to find the solution for the associated homogeneous matrix, which we know is going to be non-singular. Because this one had one solution, this one must have one solution as well. And so this matrix will reduce in the same way that the coefficient matrix of that one did. And so we're going to be left with matrix 1, 0, 0, 1. Therefore, x and y are equal to the same thing, and that's 0, because again, we have that implied column of zeros. And so in this case, the solution is xy is equal to the set of just the 0 vector. That's the trivial solution, and we can also, again, write the 0 vector as just a 0 with a vector arrow over it. And let's think about why this makes sense. Why it makes sense that if our regular matrix over here had only one solution, which was the vector negative 7, 3, then the associated homogeneous matrix will only have one solution and therefore be non-singular. If the general solution to this matrix on the left is equal to the particular solution is equal to a particular solution plus homogeneous, the particular solution is just negative 7/3. But since that is our one and only solution to this, the homogeneous solution must just be 0. Thanks for watching, and I'll see you in the next video. Bye.